Okay, welcome everyone. This is our last installment of Csaaw for the semester. We are working on organizing next semester's agenda, which includes the usual slate of speakers and a conference, a mini complexity conference in the spring. So we'll be looking for details about that. Today, Chris Miles will be telling us about optimal fluid mixing. I'll pass around the sign-in. Not actually signing in, but just a list of names of who's here sheet. If you put your name on that, that'd be great. And with that, Chris, take it away.
Okay. Hi, welcome. My name is Chris Miles. I am a physics PhD student here, and my advisor is Csaaw. Today I want to talk about optimal fluid mixing and also introduce Hack's variations. And show where that's useful. A lot of the results that I'll be showing today are from this reference, but then I'll introduce the next stage of the project, which is what I'm currently working on. Okay, so the goal is to optimize mixing. And well, first I want to just describe what it is that we're mixing. So throughout this presentation, this is the setup. So what you see here is a snapshot of a fluid, and the color is indicating the concentration of a dye. So this is like cream and coffee, for instance. So the white region represents a high concentration of this dye, and the darkest region would be the lowest concentration of the dye. And the way I'm representing the concentration at a given point is by this function theta. So it's the concentration field. So at a particular point, theta takes on a value from -1 to 1. So that is the range in concentration that it can take. So -1 would correspond to black, and 1 would be the white region. Okay. And one other thing, this is a periodic domain. So what dye comes through the top, shows up at the bottom, and likewise through this direction. Okay, so now how do we actually measure how mixed something is? So intuitively, you can kind of tell what's more mixed than the other. You kind of know it when you see it. I mean, most people would say that this is more mixed than this, and this is probably more mixed than that one. But how do we quantify that? So there are many definitions of mixing, but I'm going to present just one today. And to help us out, we're going to review some Fourier series tools that will be useful. So just as a review, when you have a periodic function just in 1D, so say you have this function, you can decompose this periodic function into simple functions like cosines and sines. And in this example, this one is just composed of sines. So I just stole this from Wikipedia, but it's an animation that visualizes this. So you can take this sine, or sorry, you can take this function and decompose it into these functions that are showing up in the background. Okay. And so this function here can be decomposed into these simple sine functions, and each one has an increase in frequency. And then on this other plane here that's showing up, right, it's showing how much does this sine wave contribute to the function, right? So these are weights for each one. So if you know this, then you can reconstruct the original function, right? So that's what Fourier series can do. So you can do the same thing in 2D. So you can take a function defined on in a 2D plane and decompose it the same way into these simple modes. So here we have some function, and here represents all the modes. So these are equivalent to those sine curves of the cell. But in 2D, they look like this. So this is only a subset of all the possible modes. But the reason why you want to decompose it into this is because it helps us with defining what we mean by mixing. So, so let's say we have this concentration, we decompose it. If we see that the weight that corresponds to, say, this mode is really high, then we would like to define that as a really well-mixed concentration. If we decompose it and we find out that the weights are heavy on these modes here, then we would say that's more unmixed. So we want a measure that kind of tells us what's going on with this decomposition. So,
Chris, quick question. Did you just qualitatively define which ones of those are better mixed? So, like, say you're looking at the one in the very center and then the one just to the right of it.
Yeah.
I guess you could say that the one to the right is better mixed, but like, how are you, when you're decomposing it, how do you get a whole score?
Yeah, I'll show that in a minute. But yeah, so this is just slightly better than that one.
By assumption or definition?
By just qualitatively.
Okay, qualitative.
Yeah, but we're going to make a precise definition in a minute. But I just want to motivate the definition of it. So, so for each one of these modes, they have an associated wave number, right? So you just take the magnitude of this vector that's showing up on top, right? And so the larger the wave number, it feels like that's a more mixed mode, right? So, okay, so now if we take a general Fourier series, this is, it can be compactly written as a complex exponential, but the same idea holds for this form. So this is the actual measure that we're defining. Now, if you study it for a bit, you'll find that if the weights are on the low wave numbers, if those are heavily weighted, then you're going to get a large number for this norm, and that means it's going to be really unmixed. Okay, and if you have a lot of weight on those higher modes with a higher wave number, that's going to correspond to a small number that's going to show up here. Okay, and so when it's small, it's well mixed, and when this number is large, it's unmixed. Okay, so that's what it'll tell you. So let's just see if it follows our intuition. So this measure that we just defined, it tells you how unmixed the concentration is. Okay? The higher the number, the more unmixed it is. So so this concentration looks more unmixed than this one, and that's also what the measure is saying as well. And so this one looks more this one looks more unmixed than that one, and so the measure is agreeing with what we expect. Okay, so now we have a definition of what we mean by this concentration, or how mixed a concentration is, or how unmixed it is. Okay, so now we can quantify what we mean by mixing, but now let's talk about stirring. So, so for stirring, what I mean is that we have control of the velocity field. So in this fluid problem, we actually don't have Navier-Stokes. So Navier-Stokes is just F equals ma for fluids. And so we're not allowing the forces to control the velocity field. We're now in control. So we're taking control of the velocity field, and that's what I mean by we're stirring the fluid. We have complete control of the velocity field. Here I have a snapshot of a fluid, and then this is a velocity field overlaid on top of the concentration field. And basically, I'm telling the dye which way to move. Right. So particle here is supposed to move this way at that instant time. So you can kind of see what happens over time. So say I have some velocity field, and that velocity field is free to change over time. And so it's almost like a wind map. You're looking at the wind, and you have particles in the wind that have a certain color, say, and they just drift with the wind. So intuitively, it's as if the concentration is just moving with the flow. So you can see that the velocity field is mostly pointing this way, so the concentration moves that way, and the velocity field is pointing this way, bottom portion, so the concentration moves that way. And so this is expressed mathematically by the advection equation. Okay, so yeah, if you know, so another way to think about it is if you had a particle sitting here, it has a color, and it just drifts with the velocity field, but it retains its color. It never changes its color. So that's another way to think about it. Another thing to notice in this video is that you never have compression in flow. What I mean by that is that you'll never see like all the black go into one point, and all the rest is white. Say. So that's what I mean by it's incompressible. Another way to say this is that all the black, the area of the black region, will remain the same later on in the flow. You'll still have the same amount of black, same amount of white. It's area preserving.
Chris?
Yeah.
Do you have any, I know this is a difficult question, any idea how things would change if it were compressible?
If it were compressible, that would give you more freedom. So
Yeah.
the optimal solution that I showed today is constrained by this, right? So there'd be more freedom to choose.
Yeah.
And what's the benefit from compressing?
From
Just like becoming like having uniform density.
Decompressing. You mean so like stretching instead of compressing? Yeah, I'm not allowing either. It's not able to. Right. So if I compress the black region, then the white region would be decompressed.
Chris, is this also on a torus, or what sort of?
The
what are the
domain-
boundaries?
Oh, the boundary conditions are periodic.
Okay.
So if dye goes through the top, it shows up through the bottom, and likewise through these sides. So, okay, so how do we enforce that constraint? That's given mathematically by this equation here. It's divergence free. Okay, so let's look at the optimization of this. So we want to, the goal is to decrease this measure, right? Because it's telling us how unmixed it is, right? So you start off with, say, a value of 1, and over time you want it to decrease by the stirring, by the control of the velocity field that you have. So, so one way to ask the question is that, okay, I give you a concentration field. What should you do at this moment in time? What's the velocity field that will decrease this number at the quickest rate? So, right, so you take a specific time. We want to pick the flow, which will have the steepest slope on this curve. So that's what we mean. And so mathematically, you can write that this way. Okay, and so so just to remind you of the constraints. So this is just keeping the flow that we choose, physical, right? So if I choose a velocity field, then theta is uniquely determined over space and time. So that just says the concentration moves with the flow, and then we're just talking about incompressible liquid. So we have this constraint, and then one other constraint is on the stirring itself. how much energy do I have to stir? And I don't have an unbounded amount of energy. I can't just vigorously stir the fluid. I have some amount that I have a bound amount. This puts a bound on that process. So, and we can choose two different kind of constraints. One's
Is it just a single velocity field for the whole run, or are you able to change your velocity fields?
So yeah, you choose a velocity field that is dependent on space and time.
Oh, okay.
Right, but it is time varying. If that's
Okay. Yep.
Yeah. Oh, so that's one way to pose the question. Another way is, I only care about what happens after an hour of this process, say, at some finite time. Like, I want to pick a velocity field over space and time such that when I come back in an hour, it's as mixed as it could possibly be, and you don't care what happened in between. You just care about the endpoint. So so for that process, we just care about this endpoint. We just want that to be as low as possible. And so it might be that the optimal flow might be really unmixed for a while, and then all of a sudden dip down. That's something that could happen. So we just care about at the end time. Okay, and in addition, we have a set of constraints for that problem as well. Okay, so the general idea. So these problems are examples of an optimal control problem. So you have some quantity that you want to minimize. And that's known as the cost functional. Right? You give me a velocity field, and then I give you a number. And that number is how unmixed something is. Right? And the U is known as a control variable, something I have control of, and theta is just telling me the state of the system over time. So this kind of reminds us of calculus in a bit, because we have this is kind of like a function, and this is a function of another function in a way, and it reminds us of calculus in the sense that we have, like, let's say we have a function of a real number, and we want to pick the x, which minimizes this f, which is similar to what we're trying to do. Instead of picking a real number, we're trying to figure out a function that will minimize this. Okay, so so what do we do in calculus? If you want to find the minimum of a function, you figure out what the candidate what the candidate solutions are, right? And those are known as extrema. You find out where the slope is 0, and I should have included the endpoints. Those are also candidate solutions. So that's what you do for calculus. But we're interested in something like this, where we have some function that is dependent on functions. So this is kind of an abstract plot, because what I'm showing here on the x-axis is functions. So every point represents a different function, right? So what we're trying to achieve is a minimum of this thing. And so calculus of variations is what helps us with that problem. Right? You give me a function, and then I give you a number for that, right? So for our case, it's you give me a velocity field, and then I can tell you how mixed it is at some finite time. Okay, so this seems like a very abstract thing, but it's not. I mean, here's a simple example of a function. If you give me a function g, and I take the integral of it, I can give you a number for that. Right? So this is an example of a function. So here I have different functions, and for each one there's a corresponding number. And in this instance, it's just the area under the curve for each one of these. Right? So that's an example of a functional. Okay, and so we're usually interested in minimizing this functional. Like what g is going to give you the minimum value? And in this example, say we're only concerned about non-negative functions for g, then that one would be just gx equals 0, say, throughout this region. That would be the minimizer. But that's not very interesting. Let's look at a more interesting example of why this would be a good thing to study. So this is a classic example from calculus of variations. So this is known as the Procrone problem. Not sure if I'm saying that right, but it means shortest time, to break it up in its roots. But the problem is this: you take a wire that goes from point A to point B, and we're free to choose its shape. And you take a bead and you put it at point A, and the bead has a hole in it, so it can travel along the wire. And so and it travels along without friction. And so you let go of that bead, and then it's free to fall along this wire. And the question is, how should I shape this wire so that I get this bead to point B in the shortest time? Right. So, right. So, I mean, you could think of maybe I should have it straight for a while and then dip down. Maybe it should accelerate really fast at the end, or maybe it shouldn't do that at the beginning. Maybe it should just be a straight line. So the question is, how should I do that? And then we can figure out how they, or we can talk about the shape of this wire as just a function, y of x, right? And so the real question is, how should I choose y to get the shortest time? Right. So now we've got to construct a function. You give me y, a function, and I'm going to give you back a number. Okay, so to tackle this problem, well, we know one thing. We know conservation of energy. So if this bead drops down a distance y, it loses some potential energy, and that goes into kinetic energy. And this is actually a positive quantity on the left-hand side, even though it's negative, because y is negative, because it's really steady origin. But anyway, we can figure out what b is, and it's just a function of y. It doesn't matter where it sits in x. And we know one other thing. It's that, so if you look at a little piece of this wire, ds, this distance, and we know it was traveling at speed v, we know how long it took to travel that small distance. Okay. Oh, and we also know what b is from conservation of energy. And we know what ds, we can relate, just take this as given, but we can relate the ds to the dx by this quantity here. Okay, so now we have our functional, we integrate on both sides of that, because now we know how the time depends on y. So you give me y, I can plug in y into this integral and integrate it and then figure out the time. So so you can use, I'm not going to show you actually how to go about using calculus of variations, but I just want to give you a gist of when you would apply it. So yeah, when you have a functional like this, you can use calculus of variations, and it tells you what which curve would be the best, which function is the best. So in this example, this blue one here is actually the optimal path for this wire. So you can see that the bead actually gets there before some of these other wires, and that's given by a parametric function. So that's how calculus of variations is used, and we do a similar technique for this harder problem. And so if we look at the local and time optimization, we can figure out what the optimal flow is, and it's given by this expression. So don't worry about the details. All you have to know is that u just depends on theta at some time. We can do some computation on the concentration field and then figure out what b should be. So let's take a look at what the optimal flow is. So here we have this at the beginning. It's really a mixed, and then let's see what happens over time. and then you can see that this measure is decreasing over time. And then we can have this constraint rather than power. Let's see what happens there. This is the solution that you get. So I didn't let it run for as long as I did on the last video because of some numerical instabilities that showed up. But so you can see that there's some fingers that are showing up here and then it explodes. But I'm trying to work on that. But I'm not sure. But what's interesting is that this flow seems to mix by some kind of budding process, but the other ones seem like more of a folding process. It's kind of an interesting takeaway. But I'm not sure if there's another bud that's showing up at a really small scale, or I need to have a higher resolution. But that's as far as I can take that simulation. So the current thing I'm working on now is global in-time optimization. So that's currently what I'm working on, and this question is global. Just to remind you, because we don't want to figure out the velocity field throughout time. It's dependent on the whole history, not just what's going on at this moment. So that's the current state. All right, so that's all I have to say. So the main result of all this is to put a bound on this mixing process, so that the engineer has realistic expectations. This is kind of like the same thought process behind the Carnot efficiency of an engine, right? You have some idealized bound on an engine, on how much work it can do, and so the engineer can't hope to get more than that. So this is, of course, an idealized setting as well, but we're hoping to put a bound on that process and say how quick. I mean, even if you had complete control of the fluid, like how well could you possibly do? And so now the engineer needs to think, okay, well, I know that's the bound, and now I need to figure out how to set up fans or how to control the fluid in a practical manner. So, yeah. So thank you for your time. Any questions?
So you mentioned like the second phase of like what you were presenting was kind of what had been done and what you're working on now. So
Yeah, I'm working on the global time.
okay, so are you working on like what you kind of just talked about sort of like the creating a bound for things, or is it something else?
We're interested in making bounds on it, but right now I am trying to just solve it numerically. So we actually have the equations that come from calculus variations. So it's like the equivalent of Euler-Lagrange equations. They're equations that need to be solved, but now it's a numerical test to actually figure out what it is, and then we can look at what's going on numerically, and then we can make some guesses on how to bound the process. So it's kind of like our experiments, right? So we run our experiments, and then we can maybe gain some insight of like how the process is going, and then it might lead us to better analysis and ways to bound the process. So that's kind of the general method.
So I think I'm missing something methodologically,
Okay.
and that might just be me missing something. You are doing some sort of machine learning on figuring out what vector fields do best, or you are hypothesizing them and supplying them to your program so that you numerically crunch them and figure out what your
No, there's no machine. There's no like data mining. We use calculus variations on this problem, And then what you get out of it is a set of equations that need to be satisfied
Okay.
for it to be. So it's kind of analogous to, say, taking the derivative in calculus.
Okay.
Okay. So you take the derivative and then you get you take the derivative of this and you set it equal to 0. That will give you candidate solutions.
Okay.
And what we're doing in our problem is we have a functional, and we take what's equivalent to a derivative, and we set it equal to 0. And then we have a set of equations that we're looking to solve, right? And then that'll give us some candidate solutions.
So like how many candidates are there? Like order of 1,000, 2?
That's a really hard problem. So it's
Yeah.
easy to find the, this is called like finding the solution to the first variation.
Okay.
But finding the global optimizer is a really hard problem. But we know that it needs to at least satisfy these conditions that we have. So it's what's known as like, these are necessary conditions, but not sufficient. Right?
Yep.
It kind of like weeds out most of the problem, or most of the possible solutions, but not all of them.
So how many solutions have you thrown at your numerical?
Well, right now we haven't even solved the equations yet to get these kind of solutions.
Okay.
That alone is hard. So that's what we're working on now.
I see.
But then we'll look at the next step. Okay, well now we know these might be, we're seeing some of these solutions. Then maybe we can deduce. Maybe there's only one. It's possible that there's only just one candidate that will show up. Right? So that'd be equivalent to calculus where you just have like x squared, and there's only one minimizer. So maybe there's some way to prove that that there's only one minimizer. So one way to see that would be maybe like our numerical scheme always converges to one solution always. Yeah. And that might give a hint that there's only one that exists. Unless, I mean, maybe you run the numerics and you get a conversion to a solution. You always get a different solution each time you run it. So that might hint at many solutions if possible.
I think you're right, John, that there are people that would approach this problem by machine learning.
Yeah. Seems inefficient.
So, you mentioned the difference between bowling and putting.
Yeah.
Is there any, like, do you have any kind of intuitions about, like mathematically, like why one might be more efficient than another, or what sort of patterns you can predict that might produce optimal heat flow?
I don't have an intuition of why one would buy. The only difference there is a different constraint, and that's a big problem.
So to me, it kind of seems like the budding. So when you're So the budding was like a solution to the global in time.
No, that was they're both local in time.
Oh, okay.
But one was for fixed energy constraint.
Okay.
And the other one was fixed power constraint. Yeah. So the constraint seemed to weigh different.
This kind of the budding seemed to like kind of expand certain regions more in order to, I guess, kind of spread them out.
Yeah,
later,
so
divide them later.
Process.
Yeah.
Yeah.
Which is interesting. So you mentioned you're only using the like an advection equation right now,
Right.
with where you control the velocity field. Do you think the solutions would be different if you were dealing with maybe changing the forces instead, or is there
Like we kept Navier-Stokes, so
Yeah.
we had control of
Yeah.
the forces. Yeah, that is a good question. Yeah, it would be different. we wouldn't be able to achieve, because that's more of a constraint. That's a tighter constraint. Because you have, in that situation, you would have controlled forces that would direct the velocity rather than direct control the velocity. So that'd be a stronger constraint. So you wouldn't be able to achieve the mixing that you see now. You'd always see something better. When we say that for that problem.
All right, well, thank you, Chris. We will reconvene next semester. Look for emails. Oh, and if you are interested in presenting yourself, please feel free to email me or Zed. Well, I guess not you anymore.
Yeah, they're email me. I'm sure.